All right, welcome back, guys. Today we are going to spend a little bit more time on polymers, just as a refresher, talk about some of the things we talked about on the Zoom yesterday, and then at the end I'm going to show you how you can use some easy to obtain supplies to make your own polymer. So let's start with just a refresher. Polymers are going to be something that is made up of monomers. So in other words, you have tons of repeating units like this. So you have unit after unit after unit after unit. Okay, so when you do that, you can just keep adding on and on and on. It's kind of like what I said in the Zoom is it's kind of like Red Rover, right? So it's all the kids are holding hands and they create a line. It's tons of repeating units. Now, if you've ever played Red Rover, it's a very intense game, but the point of the game is you send a kid from another line. So let's say I have another line of people. You send somebody from the other line to try to break through the part right here where they're holding hands. And if they do, then they get that person and you try to get all the people from one side to the other. Now, what I want to talk about today, make sure that I kind of touch on, is the idea of cross-linked. Okay? Cross-linked polymers are going to be polymers that are going to basically have extra connections. So imagine that you're playing Red Rover, but instead of having to break through one line of students, you had to break through two. And those students were also connected here and here. So you can imagine that cross-linked polymers are going to be stronger, they're going to be more dense, they're going to be less flexible, whereas other polymers have some flexibility, they have some memory to them, meaning if you bend them in one way, they'll kind of go back, whereas cross-linked polymers are going to be harder to break those bonds because you have extra connections here, 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 and all that kind of stuff. So what are some examples of cross-linked polymers? So a good example would be rubber, or most rubber that you use for cars and things like that is going to be cross-linked. And the reason why is it's more sturdy that way. Not all, naturally rubber is actually not cross-linked. And what happens is the properties are slightly different. So if the rubber is not cross-linked, so here, let me make a little chart for you. Not cross-linked. Basically, it can get really brittle and it falls apart really easily. And we don't want that, especially, I mean, our cars are traveling on this rubber, right? So we would, and it gets brittle in the cold weather. And then in the hot weather, you have different problems. It actually can get like a little bit, it can kind of stick together, and we don't want that either. So we want rubber to be cross-linked so that you can have a more sturdy material. However, the problem is now that it's cross-linked, it's harder to dispose of it. It's harder to recycle it. So you have lots and lots of tires that are kind of just sitting around unused. One of the ways that we kind of can recycle it is if you go to playgrounds, sometimes you can see kind of rubber material at the bottom of the playground. That's cross-linked rubber that is being reused for that purpose. Okay, the last thing I talked about in the Zoom was the 4 types of natural polymers that we can find. So basically, I don't know if you realize this, your book likes to focus in on a couple of really key issues for each unit. And for this one, they've been talking about plastics and how you recycle them, how you can reuse them. However, I want to make sure that you go over some natural polymers, some things that we find in living organisms, because what I mean by a natural polymer is it's going to be something that we find in cells, that it's not man-made, whereas synthetic, what that word means is it means man-made. Okay, so here are the 4 main types of polymers that you need to know. Next year, all of you guys will be in biology. So these are the 4 polymers that make up all living things. They're made up of 6 different elements that are the keys for life: carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. I always remember CHNOPS. Those are the 6 main elements, and it's just a rearrangement of these 6 elements. Occasionally you add some other things too, but it's mostly those 6 elements, which is crazy to me, that just those 6 ingredients, you get so much variety. I think it's kind of cool. Anyways, so let's start with carbohydrates. What are they used for? Short-term energy. So this is going to be short energy. That's what I put there. So carbohydrates are going to be used all the time. All of your cells are constantly breaking down sugar. Every time you breathe in, you're basically exchanging things. You're rearranging the sugar to create energy. So carbohydrates look like this, and you can remember what's in it based on the name. You have carbo, so you have carbon plus hydrate, water, H2O. So those are the materials that you're mostly going to find in a carbohydrate. So you have those bonded over and over and over and over again. You could have them really densely packed, like in something like cellulose or chitin, which is going to be what make up insects' shells and things like that. Or you can have them a little bit more scattered, like in starches and sugars or simple sugars. But carbohydrates are short-term energy. You can turn that around really quickly, which is why people who are runners can sometimes carbo load. I don't know if you've heard of that term if you're a runner. Basically, it's like the idea you eat a bunch of carbohydrates right before your race and you have extra energy. Lipids are going to be long-term energy. Okay, and these are going to be more fats and oils. So they are going to be harder for your cells to break down, but when they do, you can get a lot more energy for it. So for example, here is your lipid example. You can see the reason why it's a polymer, you see the repeating parts over and over and over again. This is where you have a difference between unsaturated and saturated fats. Saturated fats, like the one in the top, that's going to be a solid at room temperature. So those are going to be like your fats. They're a little bit less healthy, whereas your unsaturated unsaturated fat is going to be basically oils, which sounds a little bit weird, but these are going to be things that are a little bit more healthy. You need a certain amount of fats and oils in order to be healthy. Also, our hormones are actually lipids as well, so they're long-term energy. Then you have nucleic acids. Nucleic acids are going to be DNA and RNA. So basically the N and the A stand for nucleic acid there. The reason why it's polymer, you have repeating units here. And each of those repeating units has different letters in it, which tells your cells what it's made of, or what it's coding for. So basically, if you're going to kind of summarize what it's used for, it's going to be information. Okay? Then you have proteins. Proteins are going to be help with chemical reactions. Put reactions. So proteins help with chemical reactions. You are constantly doing chemical reactions inside your cells. Every time you exchange oxygen for carbon dioxide, every time you eat, every time you move, all of those things are going to boil down to proteins. They can also help transport things. They're kind of like the doers of your cells. In fact, they're so important that people, before they really realized what DNA actually did, they thought that proteins are what you pass down from parent to your child. So the information, the genetic information was traveling on proteins. We now know that's not exactly true, but proteins are super, super important for making things work, because DNA at the end of the day holds the recipe for proteins. So proteins are going to be over here. So you have these kind of structures. They can have different shapes based on what kind of monomer you have, or in other words, what kinds of paper clips you're stitching together. Then over and over and over again, you can get different shapes that can just kind of build on each other to create these enzymes and different things that can catalyze reactions. So that's the main crux of what we did in the Zoom, in case you missed it, or if you need more information. Now let's talk about making a polymer. For the first one, I have some non-fat milk, or some fat-free milk, okay? And I'm going to add to it some vinegar, and we're gonna watch what happens. So, let's see. It's about a tablespoon of vinegar, and in here I have about 7 tablespoons of fat-free milk. So let me kind of swirl this around. I don't know if you can see it, but it's starting to kind of form a solid. It's kind of grainy, and we're gonna basically filter out some of this, some of the liquid portion, and see what we get. But basically what's happening here is you have 2 different polymers that are interacting. You have the polymer that is inside the vinegar, and or really the vinegar is kind of acting as a catalyst, but there's a polymer inside of the milk, a carbohydrate, And when that happens, you're basically kind of reforming these bonds. What I'm doing now is I'm going to pour this in, and I have a coffee filter right here, so hopefully I can get the liquid portion. I'm going to kind of drain that out a little bit, and you'll see what we're left with. Even as I'm pouring this in, let's do it this way. You can see this is not just milk anymore. What's happening here is the polymer that's in milk, or casein, is clumping together because of the acidity, how acidic that vinegar is. So let's see if I can get some of this out. Basically, this product is almost like a homemade glue. Oh, I messed up. Oh no. Well, if I were to filter out, so let's see if I can get a little bit more here. Filter this out just a little bit. Basically, the product would act like a glue, and you can use it as an adhesive in different cases. I might need more sturdy coffee filters than what I have. But if you look here, this is obviously going to be a little bit different. Oh, it smells like vinegar. This is not just milk anymore. This is kind of a little bit more of a solid substance. Let's see if I can do this without getting it over my iPad. That would be gross. So let's see if I can kind of show you in the video. Let me pause it. I basically dried out my product, and so now I'm going to add a little bit of baking soda to it just to kind of make it a little bit more slimy. So about 1/4 tablespoon or so of baking soda, and then we're going to see what happens here. These two solids are going to interact, and it's going to create a little bit more of a gooier substance. Gross. But anyways, it should make a little bit more of a slime if you were to do this one at home. I'm going to show you a different slime experiment. This slime, what you need is going to be some cornstarch right here, as well as water and glue. So right now I have equal parts of cornstarch and water. I can't see super well. And it's kind of mixed together. I just put 2 tablespoons of each in here, and then you would need to put in 4 times as much glue. So I need to put in 8 tablespoons of glue. I got this special color changing glue, so we'll see if that actually works. And I'm going to add that to my mixture and see what happens. So let's see. This is what my mixture looks like right now. It actually took the whole bottle of glue because I added so much ingredient, so I should have a lot of slime here. It took the whole bottle of glue, so I had to break into the normal white glue, Elmer's glue, that is. So let's mix it up and see what happens. I'm going to actually use this same spoon right here. It's actually a tablespoon thing. This is what happens when you use glue. Okay, so let's see what happens. Ooh, it's kind of already starting to form a little bit of a polymer here. So I might actually have to get my hands and do it because it's starting to stick a little bit more than I thought it would. All right, so I let this mix in. I'm gonna let it sit for a couple minutes so it gets a little bit solidified. But this is my slime right now. The reason why it becomes that slime is because what is actually in the glue? The glue actually contains a polyvinyl alcohol, and so that is a polymer, and we're gonna see what happens. Let me let it kind of sit. So I'm waiting for my slime to work, but this is an example of a finished product. Elise actually sent this to me. I'm gonna put directions for how to make your own slime. I'm realizing that my original recipe, you would need to alter it quite a bit because I needed to keep adding cornstarch to it. It's a little bit too liquidy still. So I'll put some directions on Google Classroom in a place. This is your Friday challenge as well. You do need parent permission before I can give you credit, so just have them fill out the little parent permission slip thing, Google form attached, and you can make your own slime. So I will attach some directions for different ways that you can do that, and I'll see you next time. Bye, guys.